Good morning, everyone. So this is Dr. Venkatesh, Department of DSH, DV Raju Institute of Technology in Asapu, and our course name is Applied Physics. Topic is magnetic properties. And previous we completed last lecture we completed magnetic properties, some fundamentals like introduction, origin of magnetic moment, basic definitions like permeability, susceptibility, and relationship between the permeability as well as the susceptibility and magnetization. So these all things fundamentals we learned, and classification of the magnetic material also we discussed in the previous lecture. So types of the classification you know very well. There are three types is there. So diamagnetism, paramagnetism, as well as the ferromagnetism. So these things we discussed in the earlier class. Right now we will discuss today three topics. So that are the Weiss domain theory of ferromagnetism, and another one is the BH curve or else hysteresis curve. We can take out BH curve, hysteresis curve, and third one is the soft and hard magnetic materials. So Weiss domain theory of ferromagnetism. Previous class we completed domain theory, ferromagnetic materials. So in that ferromagnetic family, we already know we learned ferri as well as the antiferri, and ferrites family we learned. So what are the types and how the properties can influence the several applications also we have seen, we discussed in the last class earlier. So Weiss domain theory of ferromagnetism. So before going to the topic, just I am asking one question. So that is, iron is a ferromagnetic material, but why two iron rods not attract or repel to each other? What is the reason? Iron is a ferromagnetic material, but why two iron rods not attract or repel to each other? And also they have follow the Weiss domain theory. According to Weiss domain theory, spin-spin interaction is also present in that ferromagnetic material also. But these why two iron rods are not attracted to each other? So that is the reason. Is simple. We discussed that thing in the ferromagnetic materials. So in the case of the ferromagnetic materials, the domains are in the random in nature. That means random nature means, so the magnetization value is completely zero. Net magnetic moment is completely zero. So that's why the two iron rods are not attracted to each other or repel to each other. So this is the thing, interesting concept we can see in the domain theory of ferromagnetism. So what is domain theory of ferromagnetism? Weiss proposed that a concept of the domains to explain hysteresis effects observed in ferromagnetic materials, as well as he is also to explain the properties of the ferromagnetic material. He proposed the Weiss domain theory of ferromagnetism. So what is domains? What is domain theory? So if you are taking a region or a region, domain means if you see the diagram here, there is a region is there. All are regions. So one region, second region, another region. So here if you see the magnetic movements, spin magnetic movements are arranged in the domain to domain different direction. So this domain is having the different direction. Similarly, this is having different direction. But in the domain, the magnetic movements are in the same in the direction. So if you consider a region in ferro or ferrimagnetic material where all the magnetic movements are arranged in the same direction, called is known as a domain. So similar means like an example you will take. If you consider one forest, simple. So the forest is like this one, boundary is there like forest. So we know very well there are lion zones, tiger zones, as well as the snake zones and monkey zones. Everything we are seeing like a domains. So whatever the monkeys are, that are the spin alignment atoms. So these are. So similarly, we can take over this one here also. If you are considering ferromagnetic material, so in that ferromagnetic material, all the magnetic moments are aligned in the same direction. So that is known as a domain. Each domain is spontaneously magnetized. Each domain is spontaneously magnetized. Each one is the completely spontaneously magnetized. If you are applying magnetic field to this domain, then what happened? So whatever the alignment of the magnetic moments are completely towards the field direction. So they can orient in the field direction. So then this material can be magnetized. So this study we can see. Consider an unmagnetized specimen sample. So in each domain is spontaneously magnetized. So the direction of magnetization is shown below figure. So the motion of the domain walls, you can see the below figure. So here if you are applying any magnetic field to the ferromagnetic material, that can be magnetized. So initially you are not applying any magnetic field to the ferromagnetic material. So this won't be magnetized. All domains are in the different in the directions. So this is the one domain, this is another domain, the spin alignment. So is a different. So the motion of the domain walls at low values when we are applying the applied field, as well as the rotation of the domain walls at high values to the applied field. The motion of the domain walls is low value at applied magnetic field. Similarly, rotation of domains is high values at the applied magnetic field. The first diagram you can see, this is the diagram. In this diagram you can see, here we are not applying any external magnetic field to the ferromagnetic material. So the domains are all in the random in the direction. The magnetization value is also 0. This is a magnetization value. We are not applying any magnetic field. So that all domains are in the different directions. So the net magnetic momentum is completely 0 in the first case. So which is the best? Whatever the previous I asked the question. So that is this is the good answer for that one, because so all are in the different directions. So net magnetization is completely 0. Net magnetic moment is completely 0. So that's why the ferromagnetic materials, that means two iron rods will not attract or repel to each other. So if we case the second case, so here we are applying small magnetic field to the ferromagnetic samples. Small little bit magnetic field we are applying here. Then what happened? Then the magnetization value is some magnetization value we can see. So it will be increased like this. So little bit only I am providing. So it will be increased like that. So the magnetization value is increasing. So and small corresponding field, the magnetization is increasing. And domains also, rotations we can see. The domain rotations we can see. What are the domains? First to second, the rotations can be changed due to with respect of the magnetic field. Next case, I am applying more and more magnetic field. So it reaches its saturation point. It reaches its saturation point. So it reaches its saturation point. This is a saturation point. So we can see. So we are applying more and more magnetic field. The domains are completely towards the field direction. They can orient it in the field direction, and it reaches the maximum magnetization value. So that value is nothing but we can say that is a saturation magnetization of the material. So here the magnetic field is increasing continuously. There is no zero field. So here also 0, but this is small. But here also we are increased more, very large. In the case of the little bit large fields we are providing. So as compared to the second diagram. So maximum m is not equal to 0, which is having the magnetization value is the highest value S. So after some time particular, we are reducing the field to 0. The magnetic field we are reducing to the field to 0. But m is not equal to 0. So this is the some lag behind in the magnetic materials we can see. So that lag behind of the magnetization is nothing but BH curve or hysteresis loop. This is the loop. So this is the MS saturation magnetization value. This is the MR magnetic retentivity. This is the HC coercivity of the magnetic material. So in the fourth case, we can see the magnetic field is 0, but magnetization is not equal to 0. So this is the less than the maximum. This is the case, relativity case. All domains are oriented in a different direction, but these are not coming to their original motion. Domain wall motion is irreversible in the case of the fourth. So this is the case we are observing in the domain theory is completely observed by the V's. So this is for the ferromagnetic materials. So this is the case we are seeing. So next we will go for the hysteresis. Yeah, this is the domain theory of ferromagnetics. So what is domain theory? So what is domain theory? When we are applying an external magnetic field to the magnetic material, that can be magnetized. After removing of the magnetic field is also that showing some magnetization value. So this is nothing but hysteresis. So we can explain the hysteresis with the help of the domain theory also. Next topic is the hysteresis. So hysteresis means the lagging behind, some lag behind. So like a lag behind of some magnetization value is nothing but hysteresis loop. So a pure ferromagnetic sample we are taking. All the domains are in the random in direction, which means there is no magnetic moment. So net magnetic moment is 0. So the spin alignment is in the random direction. So net magnetic moment is 0. So then now we are applying an magnetic field to the ferromagnetic substance. So then automatically it can be magnetized. We are increasing the field, the magnetization value is continuously increases and it reaches its saturation point at particular whatever the value, maximum value. So then it can be reaches to the saturation. That saturation point is known as saturation magnetization. So if you see the diagram, the magnetic field strength we are providing like this as like a sinusoidal wave. It's in the form of the sinusoidal wave. So is the maxima and minima. Where the maximum value at particular A point we are receiving maximum value, for B point which is the minimum, and for C point which is negative of the maximum. So this is the magnetic field strength with respect to time we are giving. So this is the diagram. So now when we are applying a magnetic field to the magnetic material, initially the magnetization value is completely increases and it reaches the saturation value. Once it reaches the saturation value, so that is not showing more than a saturation value, because that is the maximum value. So once reaches the saturation value, that saturation value is known as a saturation magnetization. So after removing the magnetic field, so this is the thing, saturation value. All dipoles are in the same direction, and where we are applying the magnetic field, so that is the H is something, so this is not equal to 0. So then we are receiving the maximum value. The magnetization value is the M is the maximum. At that particular point is known as saturation magnetization. Next we are removing the magnetic field to the ferromagnetic material. So H is equal to 0 and M is not equal to 0. So not all domains are in the same direction, but it is showing some magnetic movement. So this type of showing some magnetic movement is known as retentivity of the ferromagnetic material, we can say. So some lag behind is going here. So this is the retentivity of the ferromagnetic material. So next, to remove this retentivity of the ferromagnetic material, we need to apply opposite field to the ferromagnetic material. So we are applying opposite field to the ferromagnetic materials to obtain the domains are in the same direction. We need to go previous direction. We want the domains in the previous direction. So that's why here we are applying negative magnetic field. So then the magnetization value can be reaches to the 0. So that value, whatever the value negative magnetic field we are providing, that means width. So the width of the loop is known as the corrosivity of the magnetic material, which will decide the entire property of the type of material. If the coercivity width, the width of the loop is very high, greater than 100 oysters, we can say that is a hard magnetic material. The width of the loop is less than the 100 oysters, we can say that is a soft magnetic material. So we are using both hard magnetic material as well as the soft magnetic material for the several applications. So the width of the whatever the ferromagnetic material is there, so that will decide the type of material. So when we are applying the opposite saturation magnetization, then here opposite magnetic field, then here H is not equal to 0 and H is negative. So M is the maximum value. All domains are in the same direction but opposite to A point. Whatever the A point is, so opposite to this A point. So we can say this is the coercivity of the magnetic material. If you see the diagram, so this loop can be like a hysteresis curve. We that can be formed. So initially we are applying the magnetic field. So it reaches to its maximum point due to with respect to field. That point is known as saturation magnetization. And after removing of the magnetic field, also which is presenting some magnetization value. So this lagging behind of some magnetization value is nothing but here we can say that is a retentivity. And later that, so to reduce this whatever the magnetization value to form a material to the original, whatever the original previous state. So definitely we need to apply opposite direction field. So then the magnetization value becomes to 0. So that this type of applying the opposite field direction is, we can say that is the coercivity of the magnetic materials. So which is the, generally we can say the coercivity is the width of the loop. Generally we can see retentivity is a height of the loop. Generally we can say the whatever the maximum point, we can say that is a saturation magnetization. In the low side is the opposite saturation magnetization value. So here this is the three types of the properties we learn from the BH curve. So it is the most important to understand the ferromagnetic material nature. So whatever the same thing, also domain theory also same thing, we can implement a domain theory to the hysteresis loop also same. So domains are in the random in the first random nature in the first condition. So when we are applying the field, so the domains can be rotations can be started and they can be aligned in the same direction to the field. So it reaches the saturation magnetization. Same thing we can apply to the magnetic domains. So all dipoles are in same direction to the opposite field is known as opposite saturation magnetization. So here MR is also there, negative side. Negative side also we are receiving. Negative side MR value, M is not equal to 0 but H is equal to 0. So same thing, M is not equal to 0 but H is equal to 0 in the positive direction, this is in the negative direction. So now we will discuss hysteresis. What is hysteresis? Lagging of magnetization behind the applied magnetic field called hysteresis. Saturation magnetization, the maximum magnetic moment of the sample, that is when all the domains are in the same direction. That means the magnetization value is equal to maximum magnetization. We can say that is known as saturation magnetization. What is retentivity? So residual magnetic moment of the sample. So that means magnetic moment retained by the sample when the magnetic field applied that is removed. So the majority of the domains are not in the same direction. So if you are removing the magnetic field also, some magnetization can be present in the sample. So that behavior is known as the retentivity, where the magnetization is not equal to 0, which is the almost less than the maximum value. 0 but less than the maximum value. So coercivity or coercive field. So it is the amount of demagnetization applied field to the destroy the retentivity of the sample. To destroy the retentivity of the sample, we can apply the magnetic field in the opposite direction. Then we will receive the coercivity value. So generally we can say that is a width of the loop you can take. So which will decide the hard and soft magnetic materials. This is important. Hysteresis loss. Due to this magnetization and demagnetization process, when the sample is subjected to the AC magnetic field, so the area of the MH loop or BH curve is called hysteresis loss. So under the area of BH or MH curve is called the hysteresis loss. For example, we are applying the magnetic field to the ferromagnetic material. So that can be we are magnetizing as well as the demagnetizing. So whatever the energy, that energy is little bit we can say in the form of the loss of the in the form of heat. So like a eddy current, nature, we can take losses also, some little bit losses also occur in ferromagnetic samples while we are magnetizing as well as the demagnetizing the sample. So that is known as the hysteresis loss. So to identify the hysteresis loss, we are already using several inductor coils. Like a fan is also we are using coils, inductor coil. Some amount of the electric field is also we are losing due to the inductor coil nature. That means in the form of the eddy current. So we are applying the electricity, then the magnetic field is also generated. That is an electromagnetic coil. That means we are applying electric field, so automatically magnetic field can be generated. So in the form of the losing, while we are magnetizing and demagnetizing process, so the energy can be in the form of the heat, we can lose some little bit energy. So that is known as hysteresis loss. It is due to the magnetization and demagnetization of the sample. When an AC magnetic field is applied, area under the MH or BH curve is called hysteresis loss. So this is the BH curve completely. Hysteresis will end. Next topic is differences between the hard and soft magnetic materials. So what are hard magnetic materials and what are soft magnetic materials? Previously I told you that so the corrosivity will be decided on the hard and soft nature of the magnetic materials. So hard nature of the magnetic material, the width will be more and more. That means there is a greater than 100 Oersted, the width of the ferromagnetic material loop is greater than the 100 Oersted. We can say that is a hard magnetic material. The width of the ferromagnetic material is less than the 100 Oersted. We can take over that is a soft magnetic material. The magnetic materials are once magnetized, they won't be demagnetized in the case of the hard magnetic materials. In the case of the soft magnetic materials, the magnetic materials which are easily magnetized and demagnetized are known as soft magnetic material. If you see the diagram here, the width of the loop is very high in the hard magnetic material. The width of the loop is low in the soft magnetic material. So this means this is having a large corrosive force, this is having the small corrosive force. So while we are taking the BH curve diagram, in the BH curve diagram, which is the material is showing the large corrosive force, so such type of materials is known as hard magnetic materials. Similarly, if you are considering the BH curve diagram for the ferromagnetic materials, a small corrosive force we can observe that. So such type of materials we can say that are the soft magnetic materials. So these are characterized by the broadness of the hysteresis loop. Similarly, both soft and hard nature can be characterized by the broadness of the hysteresis loop. So for example, in the hard magnetic materials, the corrosivity is the high value you can receive. Similarly, high remanence value also according to the previous hysteresis, whatever the topic we discussed, high corrosivity, high remanence and high susceptibility permeability values for the hard magnetic materials we can observe. So these materials are used for hard magnetic materials. Maximum we can use it for generators, loudspeakers, like that only we can use. So in the coming to these materials, soft magnetic materials having the high susceptibility and permeability, low corrosivity, low retentivity. So hard magnetic materials are having the high corrosivity, high remanence and small susceptibility, permeability, and soft magnetic materials are having the high susceptibility, high permeability as well as the low corrosivity, low retentivity values. So larger area of hysteresis loop show a part of energy of applied field is converted into the potential energy which is stored inside the material. So a larger loop indicates that when we are applying an external field to the material, so that energy can be converted into potential energy and that can be stored in the material in case of the hard magnetic material. In case of the soft magnetic material, smaller area of the hysteresis loop represents the low amount of energy lost as heat during a cycle of magnetization and demagnetization. So we can see the width loop is very low, so the energy loss is also little bit as compared to the hard magnetic materials. In the hard magnetic materials, the coercivity value is the highest value we can see. So that means the domain wall movement is difficult to owing a crystal imperfection, and is irreversible in nature. So the coercivity will decide the domain wall movement and which is difficult to owing crystal imperfection as well as the irreversible in nature. So that means once we are magnetize the ferromagnetic material, hard magnetic material especially, so that won't be demagnetized. So that are in the irreversible in nature. So here in the soft magnetic material, the coercivity value is low. They can easily, we can see the movement of domain walls with respect to magnetic field, and these also in the reversible in nature. So in these materials, the irregularities like mechanical strains will be more. In these materials, the irregularities like mechanical strains will be more. These materials are free from the irregularities like impurities, soft magnetic materials. So while we are considering the hard magnetic materials, the irregularities, so mechanical strains we can see more and more in the hard magnetic material. Coming to the soft magnetic materials, these materials are free from irregularities like impurities. So very less type of mechanical strains see in the soft magnetic materials. So the examples for the hard magnetic materials are, these are the permanent magnets, and we are using these permanent magnets in loudspeakers, microphones, generators, and to lift the crane vehicles in the cranes also some electromagnets we are applying. So here in the case of the soft magnetic materials, power transformers, ferrites. So these ferrites we are using for the better memory as well as the sensor applications. Electromagnetic circuits, power transformers, we are using the soft magnetic materials. So these are the major differences between the soft and hard magnetic materials. So soft magnetic materials means the width of the loop is less than the 100 Oersted coercivity. So in the hard magnetic material, which is the greater than the 100 Oersted. So this is the major difference between the soft as well as the hard magnetic materials. So now we will discuss the variations in the hysteresis curve. So if you see the diagrams, so the hard and soft magnetic materials, so we can see in the diagram here, so there is a considerable variation in the hysteresis for the different magnetic materials now I am considering. So for in the diagram here, we are applying magnetic field, the magnetization is also more. So here the whatever the retains large fraction of the, here M value is the retains large fraction of the saturation field when driving field removed. And the field is removed, so there is a large fraction of saturation magnetization we can see here. And also the width is very high. So which is desirable for the permanent magnets and magnetic recording media memory applications. We are using this type of hard magnetic material especially. So memory and magnetic recording media, we are using this type of large amount of the coercive field hard magnetic materials. In the case of the second diagram, we are applying the magnetization, we are applying the magnetic field corresponding, the magnetization is also increased. So after a particular time, the saturation magnetization can be generated. So this is the saturation magnetization value. The entire entire 3 diagrams saturation magnetism MS. So this is the B value, entire magnetic field value, whatever the B we are applying. So the area of the hysteresis loop is related to the amount of energy dissipation upon reversal of the field. The area of the loop, whatever the hysteresis loop is, related to the amount of energy dissipation upon reversal of the field. So the reversal of the field is a dissipation is also we can see. Now coming to the third, so there is a narrow in the hysteresis loop, we can see narrow hysteresis loop, which implies a small amount of dissipated energy, in repeatedly reversing the magnetization. So that the desirable for which are useful for the transformers, motors, as well as everywhere electronic devices, electronic applications, we are using soft magnetic materials. So these are the major differences between the hard as well as the soft magnetic materials. So I think you will understand today. So today's whatever the outputs we receive. So first one is the domain theory of the ferromagnetism, and second one is the domain theory of ferromagnetism, and second one is the BH curve or hysteresis loop, and third one what we completed, third one is the hard and soft magnetic materials. Hard and soft magnetic materials. I hope you understand these three concepts of domain theory of the ferromagnetism, BH curve, as well as a hard and soft magnetic materials. So tomorrow we will discuss magnetoresistance, magnetostriction of the materials. So okay, thank you everyone.
Like, share and subscribe. Hit the bell icon for more updates.